We operate under the assumption that our safety systems are proactive. We believe that along the thousands of miles of American rail, the network of sensors and wayside detectors acts as an intelligent shield, constantly analyzing data to stop a disaster before it begins. We trust that if a train is moving and no alarms are sounding, it is because the train is safe. But the transcripts from the National Transportation Safety Board investigation into the East Palestine derailment suggest this belief is fundamentally flawed. The testimony didn't just reveal a mechanical failure, it exposed a systemic blind spot in how we monitor danger. The records show that the technology wasn't failing to read the temperature, it was failing to understand what the temperature meant. We were relying on a digital safety net that was programmed to ignore the fire until it was already burning down the house. You're watching Rust and Thunder, where the wreckage reveals the truth. If you value this depth of forensic analysis, subscribing ensures you don't miss the next investigation. To understand the gravity of the testimony delivered in the NTSB hearing room, we first have to reconstruct the physical reality of February 3, 2023. Norfolk Southern Train 32N was a massive industrial organism, a general merchandise freight train stretching nearly 2 miles long, weighing 18,000 tons. It was hauling a complex mix of cargo, including hazardous materials like vinyl chloride, combustible liquids, and benzene residue. But the catastrophe didn't begin with the chemicals in the tank cars. It began with a single mechanical component on the 23rd car, a standard 6 by 11-inch roller bearing. In the sanitized environment of the hearing, the NTSB investigators focused heavily on the physics of this specific component. A train wheel bearing is a sealed unit designed to endure immense stress. It carries the weight of the car and the dynamic forces of the track, spinning hundreds of times per minute. Under normal conditions, friction generates heat, and the bearing grease dissipates it. It is a balanced equation of thermal energy. However, the hearing records highlight a terrifying characteristic of bearing failure. It is not linear. It is exponential. Once the internal geometry of the bearing is compromised, perhaps by a microscopic spall or a fatigue crack, the friction begins to feed on itself. The heat liquefies the grease, the metal expands, the friction increases, and the temperature spikes vertically. This is where the hotbox detectors, the wayside monitoring systems, are supposed to intervene. These devices are infrared scanners positioned alongside the tracks, looking up at the passing wheel bearings to measure their radiated heat relative to the ambient air temperature. The assumption, the one that was quietly dismantled during the questioning, was that these detectors provide a complete picture of the train's health. The reality was far more fragmented. As Train 32N traversed the Ohio landscape that evening, it passed 3 distinct wayside detectors in the hour leading up to the derailment. The data recovered from the signal logs paints a picture of a mechanical runaway event that was invisible to the crew in the cab. At the first detector in East Palestine's neighboring vicinity, roughly 30 miles from the crash site, the bearing on the 23rd car registered a temperature of 38 degrees Fahrenheit above ambient. In the context of heavy rail, 38 degrees is negligible. It is a warm cup of coffee. It triggers no alarms. The system sees this as green. The crew sees nothing. The train continued. The friction inside the sealed housing was now overcoming the lubricant. Metal was beginning to grind against metal. 19 miles later, the train passed the second detector at Salem, Ohio. The sensor read the heat signature again. This time, the bearing was 103 degrees above ambient. This is a significant jump. The temperature had nearly tripled in less than 20 minutes. Yet, inside the locomotive cab, the radio remained silent. No alarm sounded. No lights flashed. The train was still considered safe by the algorithm governing the line. During the NTSB hearing, this specific moment became a focal point of intense scrutiny. The investigators questioned the representatives from the railroad and the signal department about the critical thresholds. The testimony revealed that the alarm threshold for a hot wheel or hotbox was set at roughly 170 to 200 degrees above ambient depending on the specific railroad's policy, with critical stops often mandated only at even higher temperatures. At 103 degrees, the bearing was literally cooking itself, but because it hadn't yet crossed the arbitrary line drawn in the software code, it was classified as a non-event. The system was designed to catch a failure that had already happened, not one that was developing. The tragedy lies in the final leg of the journey. Between Salem and East Palestine, the bearing entered the terminal phase of failure. The internal rollers likely seized or disintegrated. The heat generation went vertical. By the time the train reached the third detector in East Palestine, the bearing was glowing. The sensor registered a reading of 253 degrees above ambient. This finally triggered the critical alarm. The automated voice shouted over the radio, instructing the crew to stop the train immediately for inspection. But physics does not wait for protocol. The bearing had already failed structurally. The axle lost its integrity, the wheel set dropped, and the 23rd car dragged the rest of the consist off the rails, igniting the inferno that would poison the town. The NTSB hearing room is usually a place of dry technicality, but the tension regarding the hotbox data was palpable. The investigators drilled down into a concept that seems obvious in hindsight but was absent from the automated logic, trend analysis. Why, the board asked, did the system not flag the rate of change? If a bearing jumps from 38 degrees to 103 degrees in 20 minutes, that indicates a catastrophic trend, regardless of whether it hit the absolute maximum limit. The bearing was clearly screaming that it was dying, but the detector network was deaf to the scream. It was only listening for the death rattle. The testimony exposed that these detectors are often islands of data. In many legacy configurations, Detector A does not necessarily talk to Detector B to compare notes in real time. Each scanner takes a snapshot, checks it against a static number, and clears the train. There was no algorithmic overseer looking at the slope of the temperature graph. The assumption was that a single snapshot was enough to ensure safety. The hearing shattered that assumption. It laid bare the fact that 19th century mechanical forces were being monitored by 20th century logic, leaving 21st century communities vulnerable. Witnesses from the signal unions and safety experts testified that the railroads had the capability to monitor these trends, to see the warm bearings before they became hot. But setting the threshold lower or flagging rapid temperature rises would result in more train stoppages. It would mean more false positives. It would mean slower velocity across the network. The hearing records suggest a calculated risk assessment. Keep the trains moving until the data is undeniable. In East Palestine, the data became undeniable exactly one detector too late. This revelation forces us to look at the entire railway infrastructure differently. We see the tracks and the signals and assume a monolithic, omniscient safety culture. But the transcripts reveal a fragmented system where compliance does not always equal safety. The train was compliant at Salem. It was compliant right up until the moment it wasn't. The investigation highlighted that the distance between detectors, often 10, 15, or 20 miles, is a massive blind spot when a bearing enters thermal runaway. A bearing can go from functional to molten in fewer miles than the gap between sensors. As we wade deeper into the official records of this hearing, we begin to see the human cost of this technical oversight. The crew did exactly what they were trained to do. They relied on the machine. They trusted the silence. The NTSB panel's questioning made it clear that the crew was essentially flying blind, piloting an 18,000-ton bomb through residential neighborhoods, unaware that a fuse had been lit back in Salem. The failure wasn't that the detector didn't work. It was that the detector was asking the wrong question. It asked, "Is this bearing on fire right now?" instead of asking, "Is this bearing about to fail?" The implications of this distinction are what we will explore next. The hearing didn't just stop at the temperature readings. It went into the maintenance records, the history of the car, and the decision-making hierarchy that prioritizes velocity over granular data analysis. The hotbox detector assumption that we are watching and therefore we are safe was the first casualty of the East Palestine derailment. And as the NTSB investigators peeled back the layers, they found that this assumption wasn't an accident. It was a policy. That policy was buried deep within the operating manuals of Norfolk Southern, a document that NTSB board members would later project onto the screens of the East Palestine High School gymnasium during the investigative hearing. It wasn't a policy of malice, but one of calculated risk, a mathematical wager that placed the integrity of a wheel bearing against the velocity of modern commerce. The hearing room was stiflingly quiet as investigators turned their attention to the specific mechanics of the wayside detection network. To the layperson, a sensor is a safeguard. To the railroad, as the testimony revealed, a sensor is merely a filter, designed as much to keep trains moving as it is to stop them. The investigation centered on the sequence of 3 hot bearing detectors, or HBDs, that Train 32N passed in the hour leading up to the catastrophe. The data pulled from the black box created a chilling timeline, not of sudden failure, but of a slow, screaming escalation that the system was programmed to ignore. 30 miles out from East Palestine, the first detector at Salem caught a reading on the 23rd car. The bearing was heating up. It registered 38 degrees above the ambient temperature. In the world of friction and steel, this is the first whisper of a problem. But inside the locomotive, the crew heard nothing. The console remained dark. The radio remained silent. The algorithm controlling the line had decided that 38 degrees was statistically insignificant, a variance that did not require human intervention. 20 miles later, at the next detector in Harpster, the heat signature had nearly tripled. The bearing was now burning at 103 degrees above ambient. At this stage, the grease inside the sealed assembly is beginning to liquefy and degrade. The metal rollers are expanding, grinding against the race, generating a thermal runaway effect. Yet, the train roared past the sensor at track speed. Again, the crew received no warning. The hearing exposed the rigid binary logic of the safety protocols. The threshold for a critical alarm, the kind that forces a train to stop immediately, was set significantly higher. Because the reading hadn't technically crossed that arbitrary red line, the system treated a failing bearing exactly the same as a healthy one. The computer saw the fire starting, and it let the train proceed. This is where the NTSB panel began to drill down, dismantling the industry's defense of these threshold settings. During the questioning, it became evident that these numbers, the specific temperatures that trigger an alarm, were not derived from the failure point of the metal itself. They were derived from operational averages. If you set the sensors too low, you stop too many trains. You disrupt the network. You lose money on false alarms. So, the safety limit is raised to the absolute brink of disaster to ensure efficiency. It is a philosophy that works perfectly, right up until the moment it doesn't. If you value this kind of forensic breakdown, where we look past the headlines and into the engineering data that actually drives these disasters, taking a second to like this video helps these investigations reach a wider audience. The interrogation turned to the concept of trend analysis. This was the smoking gun of the hearing. Investigators pointed out that the singular temperature reading at any given detector is only half the story. The rate of change is far more indicative of danger. A bearing that jumps from 38 degrees to 103 degrees in 20 miles is in the process of catastrophic failure. It is screaming for help. But the wayside detectors on this line were not networked to communicate with each other in real time to analyze trends. They were isolated sentinels, each one unaware of what the previous one had seen. The detector at Harpster didn't know the bearing had tripled in heat. It only knew the current temperature was still, technically, below the panic threshold. The transcript of the hearing shows a palpable frustration from the NTSB chair as this archaic architecture was laid bare. We live in an era where our phones can predict traffic patterns based on real-time satellite data. Yet a freight train carrying hazardous vinyl chloride was relying on sensors that operated with zero memory of the previous mile. The Hotbox Detector assumption relies on the belief that the safety net is intelligent. The hearing proved it was effectively amnesiac. By the time Train 32N reached the final detector in East Palestine, the physics of the situation had moved beyond the realm of prevention and into the realm of inevitability. The bearing was now glowing white-hot. The sensor finally registered a reading of 253 degrees above ambient. This was the critical breach. The algorithm finally triggered. The alarm screamed into the locomotive cab, a piercing digital shriek that shattered the routine of the night. The engineer immediately throttled down and applied the brakes. But the hearing records highlight a terrifying reality about braking physics and reaction times. The alarm sounded only after the train had passed the sensor. The train was moving at 47 miles per hour. By the time the crew received the message, processed the emergency, and initiated the stop, The train had already traveled nearly a mile past the point of detection. The friction in the wheel bearing had become so intense that the axle itself was disintegrating. The metal had turned to liquid. The wheel set, no longer able to support the weight of the hopper car, collapsed. The derailment didn't happen because the crew failed. It happened because the crew was placed in an impossible timeline. They were given a warning only when the disaster was already in progress. The NTSB investigators focused heavily on this lag, the gap between detection and notification. In the sterile environment of a corporate boardroom, a few seconds of data transmission delay seems negligible. On the rails, with thousands of tons of momentum carrying hazardous materials, those seconds are the difference between a controlled stop and an inferno. Witness testimony from the signal engineers revealed that the system was working as designed. And that phrase, as designed, became the most damning indictment of the entire proceeding. If a system is designed to let a bearing burn for 50 miles, watching it degrade from a minor issue to a critical failure without alerting the humans at the controls, then the design itself is the hazard. The assumption that technology provides a shield was stripped away, revealing that the shield was full of holes calculated by actuaries. The hearing also touched on the aftermath of the alert. When the crew finally stopped the train, they were following the rulebook. They disembarked to inspect. But by then, the fire had spread. The heat from the failed bearing had ignited the undercarriage. The pileup had begun. The official records show that the Hotbox system, the primary defense against this exact scenario, had technically functioned. It detected the heat. It sent the signal. It logged the data. By the letter of the law, the railroad had complied with safety standards. But the standard was reactive, not proactive. It was a system built to document a crash, not to prevent one. As the days of the hearing wore on, the focus shifted from the mechanics of the sensors to the culture that set their parameters. Documents entered into evidence showed that the railroad industry had successfully lobbied for years to keep these detector thresholds unregulated by the federal government. They argued that they knew best how to manage the health of their rolling stock. They argued that internal policies were sufficient. The East Palestine chart, showing that jagged, upward spike in temperature unchecked by intervention, was the silent rebuttal to years of deregulation. The tension in the room was not just about a single accident in Ohio. It was about the realization that this same algorithm, this same silence until crisis logic, was monitoring tens of thousands of miles of track across the continent. Every day, trains pass these sensors, and every day, bearings heat up. The question the NTSB posed was simple yet devastating. How many other bearings are currently burning just below the threshold? How many other crews are driving blindly into a derailment because the computer hasn't decided it's serious enough to mention yet? This was the pivot point of the investigation. It moved from a technical analysis of a single mechanical failure to a systemic critique of the entire railway safety philosophy. The Hotbox detector was supposed to be the eyes of the operation. Instead, the hearing suggested it was functioning more like a blindfold, giving the crew a false sense of security while the components beneath them slowly turned to shrapnel. The data was there. The warning signs were clear, but the system was deaf to the nuance of danger, tuned only to the frequency of catastrophe. And by the time it finally spoke, it was too late to do anything but brace for impact. There is a comfortable narrative we are often sold, that technology acts as a shield, an unblinking eye that catches every anomaly before it becomes a tragedy. We believe that when a train passes a sensor, it is being certified as safe. But the testimony gathered in the sterile, fluorescent-lit rooms of Washington, D.C. suggests that this belief is not just optimistic, it is manufactured. The records imply that the safety net was never designed to catch a falling star, only to measure how fast it was burning. The immediate aftermath of the derailment was a chaotic blur of physics and chemistry, but the true forensic story began months later, inside the quiet, controlled environment of the National Transportation Safety Board hearing. Here, the roar of the fire was replaced by the rustle of paper and the click of projectors displaying thermal graphs. The focus narrowed entirely to the wayside defect detectors, the Hotbox network. The investigation revealed that the crew had passed a detector just 20 miles prior to the derailment point. At that moment, the bearing was already failing, already tearing itself apart at a molecular level, yet the system remained silent. The train was cleared to proceed at track speed, carrying its volatile cargo into the heart of a residential zone, because the algorithm governing the sensors was looking for a specific threshold that the fire hadn't yet reached. This is where the NTSB panel began to dismantle the hotbox assumption. The prevailing logic in the railway industry has long been that bearing failure is a linear process. The assumption is that a component heats up gradually, giving the crew and the dispatchers ample time, perhaps 50 or 100 miles, to notice the trend, slow the train, and set out the car. The data presented at the hearing shattered this model. The bearing in question did not heat up in a linear line. It underwent what engineers call thermal runaway. In the span of those final 20 miles, the temperature didn't just climb, it spiked exponentially. The friction generated enough heat to liquefy the metal, causing the axle to lose its structural integrity before the next sensor could ever take a reading. The system was designed to catch a slow burn, but it was completely blind to a rapid meltdown. The transcripts from the hearing show a tense exchange regarding the spacing of these detectors. There is no federal regulation mandating exactly how far apart hotbox detectors must be placed. It is left to the discretion of the railroads, governed by internal guidelines rather than federal law. On this specific stretch of track, the gap was wide enough that a bearing could transition from warm to catastrophic without ever triggering an alarm. The investigators pointed out that previous detectors had shown the bearing temperature rising 38 degrees above ambient, then 103 degrees. But because these numbers fell below the railroad's arbitrary critical threshold, no stop command was issued. The data was there, screaming that something was wrong, but the protocol was programmed to ignore it until it was too late. If uncovering these layers of industrial oversight helps you understand the complex machinery behind the headlines, a like on this video ensures we can continue digging into these dense official records. The hearing further exposed that the crew in the cab was effectively flying blind. They had no real-time dashboard showing them the temperature of individual axles. They were entirely dependent on an automated voice over the radio to tell them if a threshold had been crossed. When the alarm finally sounded, it wasn't a warning. It was a notification of disaster. The train was already off the rails. The testimony highlighted a terrifying disconnect between the data available to the back-office algorithms and the reality experienced by the engineers on the ground. The people with the power to stop the train, the crew, were the last to know the train was dying. As the NTSB board members pressed the railway executives, the conversation shifted to the burn decision. With the wreckage piled up and the chemical tankers compromised, the decision was made to vent and burn the vinyl chloride to prevent a massive explosion. Believe. The hearing documents paint a picture of immense pressure and incomplete information. The decision-makers were operating under the assumption that the tankers were undergoing a chemical reaction that would lead to a detonation. However, later analysis suggested that the temperature inside the tanks might have been stabilizing. The fog of war that descends on a disaster site meant that the choice to unleash a toxic plume over the town was made based on fear of a worse alternative, an alternative that might not have actually existed. This brings us to the most unsettling revelation of the entire inquiry: the normalization of risk. The hearing made it clear that the failure wasn't just mechanical. It was cultural. The thresholds for stopping a train had been raised over the years to prioritize efficiency. Stopping a massive freight train is expensive and disruptive to the network. Therefore, the danger zone was redefined. What was once considered a critical temperature became merely a monitor closely situation. The safety margins had been shaved down, inch by inch, year by year, until there was no margin left. The hotbox detector didn't fail to work. It worked exactly as it was programmed. It failed to protect the train because the parameters were set to protect the schedule. The final report from the NTSB was scathing. It called for a complete overhaul of how bearing failures are monitored. It recommended shorter distances between detectors, lower temperature thresholds for alarms, and, crucially, real-time data access for the crews. But recommendations are just words on paper until they are codified into law. The industry pushed back, citing the rarity of such accidents and the high cost of implementation. They argued that the system works 99.9% of the time. But in the world of heavy freight and hazardous materials, that 0.1% is not just a statistic. It is a crater in the ground. It is a town evacuated. It is a legacy of poisoned soil and shattered trust. The legacy of this hearing is the destruction of the assumption that compliance equals safety. The railroad was compliant with existing rules. The train was operated within legal limits. The detectors functioned according to their design. And yet, disaster occurred. This proves that the regulatory framework itself was lagging behind the physics of the machinery. The hotbox detector assumption, that we can predict failure with perfect accuracy, was exposed as a fallacy. We are managing massive kinetic energy with reactive systems, hoping that the sensors catch the problem before the laws of thermodynamics take over. As the hearing concluded and the lights in the room were dimmed, the final takeaway was not about a single broken axle, but about the fragility of the entire logistical spine of the nation. We rely on these trains to move the economy, but we have allowed the systems that guard them to become complacent. The warning signs were always there, buried in the data trends, ignored by the algorithms, and unseen by the crew. The crash was not an unpredictable act of God. It was the inevitable result of a system tuned for velocity rather than vigilance. Until the industry accepts that safety requires redundancy, and that redundancy costs money, the next bearing is already heating up, somewhere out there in the dark, ticking toward a temperature that the sensors aren't programmed to catch until the smoke is already rising.